Let's dive into what I refer to as our alternating series test. Now, given an alternating series, that is to say a series that can be expressed in this form or this form, I have these two forms because in this form, I start off with a negative term. Here, I start off with a positive term. That's the only distinction. But this negative 1 to the power here or here is really what's changing sign of each and every term. And so that being the case, I'll consider a sub n as a positive value. Now, the alternating series test has two premises. Number one, if the a sub n is the nth term of a sequence that's decreasing, and number two, the limit of the nth term of this underlying sequence is equal to 0, then that alternating series here or here converges. So let's be a little careful. If both these conditions are met, the series up here converges, but if either one of these two conditions or both of them are not met, the alternating series test gives you no conclusion. I can never use the alternating series test to conclude that a series actually diverges. So keep that in mind. Now, whoops. Let me get my computer out of the way. So there's an alternating series, and note that a sub n is nothing more than this. So the a sub n is simply scraping off the sign change for each and every term. Now, using the alternating series test, because it is an alternating series, and by the way, I should have mentioned this is the first time I'm considering a series that don't always have positive terms, like with the integral test, comparison test, and limit comparison test. So to determine if this particular series converges with the alternating series test, I need to check that a sub n is at least as big as a sub n plus 1 for all values of n. However, this is this fraction. This is this fraction. Both these fractions have the same numerator, but this denominator here is larger. That means necessarily this fraction right here is smaller than that. So I certainly have a decreasing sequence where a sub n is the nth term of the sequence. However, part 2, if I take the limit of my a sub n, clearly that's equal to 0. And since both conditions are met for the alternating series test, I will now conclude that the series converges. Now, before I leave this one alone, make sure you understand what's really going on here. Here is my harmonic sequence. It converges. Here is my harmonic series. It diverges. We've already shown those two. But now, all of a sudden, with this first example of an alternating series, I now see that the alternating harmonic series actually converges. So keep all that in mind. Something else. If I do have an alternating series, and I use the first n terms of it to approximate the infinite series, then the next term, or shall I say the first unused term in absolute values, is an upper bound on the error in you using the first n terms to approximate that infinite series. That can be rather useful, and it will be. I might lose